as discrete functions. We'll get into what those words mean in a second, discrete that is, but for now just sequences. We use the word sequence pretty regularly whenever the order in which events occur is important. So as a child in grade 1 and 2, you probably got some exercises where you had to determine the sequence of events. So what I've drawn here is just a list of things you might do in getting to bed and getting to sleep, and you would do them in a particular order. The order that you do them in is the sequence. So if I think about it for me, maybe it's 1, 2, 3, 4. That's the order in which I would do something. It's a sequence. As you got older and you started working with numbers, you probably saw sequences like this, 5, 10, 15, in a question that said, what are the next 3 values in the sequence? And you would have to say, oh, it's 20, 25, 30. And there we have a sequence. Okay, you don't need to take those notes. Hopefully that's pretty easy for you. And we'll work on what we're going to use the word sequence for is really the same thing. It's going to be an ordered list of numbers that's identified by a pattern or a rule, just like you can see the pattern here, +5, +5, +5. So a couple of notes on the word sequence. And I'm going to try just to stay to the left side of your page so we can use the right side to draw a table of values and give us a bit more experience with this concept. This is an ordered list of numbers. An ordered list of numbers identified by a pattern or rule. And then a little side note, it may stop, so the pattern may stop at some point, or continue indefinitely. Okay, a couple of examples. Let's just pick, we'll start at 3 and we'll add 4. And if we stop, then this is a pattern that has a definite start and finish. Let's try another one. Start at 2 and multiply by 3 to get the next term. And if I put a comma, dot, 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 that indicates that this pattern will continue. It doesn't stop at 54. That's just all the information we need in order to determine the rule for the sequence, which actually keeps on going. Okay? A sequence can also be so this should be fairly familiar to us, okay? We can also use the word sequence when we're talking about a function, and sequences as discrete functions. This is a function whose domain is the set. A function whose domain is the set or a subset. Subset means it falls within the original set. So it's a set or a subset of the natural numbers whose range is the terms of the sequence. All right, that's a bit of a mouthful, but again, we're talking about functions. So right away, you're getting back to domain and range, or when we used to use mapping diagrams, domain maps to the range, right? Well, you can see that if we consider just this sequence here, okay, there are 4 terms, and the terms of the sequence indicate the range. Well, what's the domain? Well, the domain is the number, is the term number, okay? So each of these is called a term. You have term 1, term 2, term 3, and term 4. In this one, you would have term 1, 2, 3, 4, 5, 6, and onward, okay? So the domain is the term number. The range is the set of values that are actually making up the sequence, all right? So we've got domain is the subset of natural numbers. That's 1, 2, 3, etc. And the range comes from the sequence itself. A couple more terms here, and I'm not going to bother actually saving the right side. I'm going to use it because I already kind of explained what I was going to do in the table right here and right here. So we already have a pretty good understanding of that. The next word that we need is terms. And we should indicate that those are of a sequence. Terms of a sequence, not, for instance, terms of a polynomial. Terms of a sequence. Well, a term is a single value or object. A single value or object in a sequence. So each of these are terms. 3, 7, 11, 15, they're each terms. And then we have a couple of ways of explaining these functions. One way to do it is using an explicit formula. We'll do the definition and then we'll talk about it. This is a formula that represents any term in a sequence, relative to the term number. And the term number will be designated n, where n is a set or a subset of the natural numbers, okay? A set or a subset of the natural numbers, it just means in this first example where there's a start and a stop, this only has term number 1, 2, 3, 4. That's a subset of the natural numbers. This sequence goes on forever. Its domain is all the natural numbers, 1, 2, 3, 4, 5, 6, 7, etc., to positive infinity, okay? So that's why we have a set or a subset. It starts at 1, counts ordinally, and either stops or keeps going. That term number is going to be indicated by n, and the value of that term is indicated by that right there, okay? T sub n, all right? So then what is an explicit formula? Well, it's a formula that gets us straight from n. It relates n to the value of its term. So let's just take this guy for a second. Let's say we're in this top sequence here, and in order to find any term, we simply have each time. So this is 3, which is our starting value, plus 4 times n minus 1. What does that mean? Well, n is the term number. So if I wanted to find the third term, which we already know has a value of 11, but if I wanted to find that out, I would simply put a 3 in here, subtract 1, 3 minus 1 is 2, times 4, that's 8, plus 3, 11. Okay, let's see if it works for the next one. To put 4 in there, I get 3 in the brackets, times 4 is 12, plus 3 is 15. Okay, so this would be an example of an explicit formula for this sequence right here. I can get any term in the sequence just by using its term number. In example 1, we are asked to use an explicit formula to write the terms in the sequence. So we're given the explicit formula, and we have to write the first 3 terms of the sequence, given the explicit formula for the nth term. So the explicit formula for the nth term means we can use this to figure out the value of any term. We just need to figure out the value of the first term, the value of the second term and the value of the third term. And to do that, I just use this formula, and wherever there's an n, I plug in the n that I'm looking for. So here we're going to have 3 times the square of 1 minus 1. 1 squared is 1, times 3 is 3, 3 minus 1 is 2. What about the second term? 3 times the square of 2 minus 1. 4 times 3, 12, minus 1, 11. Again, sub in n of 3, square it, minus 1, 9, 27, 26. And there we have it. The first 3 terms are 2, 11, and 26. Not much to it when they already give you the explicit formula, and you just need to plug in the value of n for the first 3 terms. So here we go. Here's another one. We've got n minus 1 over n. And we're going to find that out for the first term, the second term, and the third term. And again, we just substitute the value for n. We're told that we're looking for the first term, so n is 1. 1 minus 1 over 1, 0. So here for our second term, we have 2 minus 1 over 2. So I have the n in the numerator and the denominator, 2 and 2. So we have 2 minus 1 is 1. 1 over 2 is 1/2. And for the third term, we have 3 minus 1 over 3. 3 minus 1 is 2. That's 2/3. And there you have the first 3 terms are 0, 1/2, and 2/3. In example 2, we are going to determine an explicit formula in function notation for a given sequence. So in A, we have the sequence 7, 12, 17, 22. And we're actually going to use a very similar strategy to how we would have determined whether a given equation was linear, quadratic, cubic, or other. Those kinds of questions. So for each sequence, we're going to make a table of values using the term, number, and term, calculate the finite differences, and then graph the sequence using the ordered pairs, and determine an explicit formula for the nth term. All right, here we go. We've got our term number, n. We have our term, which is t of n. And then over here, we're going to have our first differences. And if we need to, we'll go on to second differences. So our term numbers are the subset of natural numbers. 1, 2, 3, 4 is all we'll need. That's all we're given. Though we could predict the next numbers pretty easily in this one. The term value, the actual numbers in the sequence, are 7, 12, 17, and 22. And now we're going to calculate the first differences. So we've got 12 take away 7, 17 take away 12, 22 take away 17, and in each case the first difference is 5. If we have a constant first difference, then we know that this graph is going to be linear. Let's go ahead and graph it here. Just a small sketch will be enough. X, which is not X, our horizontal axis, is our term number. Our vertical axis is the term itself. Okay, term number 1, 2, 3, 4. That's good enough. And going up here, the highest number we have here is 22, so maybe I'd go up to 30. Let's just say 30, 20, 10, something like that. And now we're going to plot our coordinates. The coordinates that we're looking at are n t sub n, okay? The term number and its term, or the value from the domain that maps to the specific value in the range. So here we have 1, 7, all right, 2, 12, all right, 3, 17, all right, 4, 22, all right, okay? So the graph models a function since there is exactly one value from the range for each value in the domain. And the function is linear, as you can see mostly from my quick diagram here. And you can also see that here. Because the first differences are constant, we know that this graph is linear. So the rate of change, or the slope, is 5. We're going up 5 over 1, up 5 over 1, up 5 over 1. Okay, so the slope of this linear function is 5. So if we had a function with respect to the term number, then it would be 5n plus b. What we don't have here is our initial value, or what would be term number 0. So we need to think about that. And just by looking at it, you can kind of see, well, if I went backwards 1, I'd have to go down 5, and that would bring me from 7 to 2. So our y-intercept is 2. So by inspection, comma, b equals 2. Therefore, f with respect to n is equal to 5n plus 2. And we put a little catch there where n belongs to the set of natural numbers. All right, that one wasn't so tough because it was linear. You can probably see where we were going before we got there. But this right here is an explicit formula that could be used for this term to get any term from its term number. If you wanted the 482nd term in this sequence, you could get it. 5 times 482 plus 2, okay? And you would get the value of that term. Gets a little trickier in B. All right, in example B, we're given 2B. We're given a sequence with an indefinite length, goes forever. And we're going to figure out an explicit formula for this guy. So we're going to do it the same way. We're going to start with a table of values relating our domain n, which is the set of natural numbers, just the term numbers, to the actual values of in the sequence, 1, 10, 25, 46. And we're going to go ahead and find the first differences. 10 minus 1 is 9. 25 minus 10 is 15. 46 minus 25 is 21. That didn't help us. So let's keep going. Second differences. 15 take away 9 is 6. 21 take away 15 is 6. We end up with a constant in our second difference. Think back to what that tells us. Because the second differences are constant, because the second differences are constant. What kind of function is this? This function is quadratic. And here's a little trick we need to know. Half of the value of the second difference corresponds to the value of a. Okay? So in ax squared, or we should be using n, I suppose, in the function with respect to n equals a n squared plus bn plus c, half of, or maybe let's even do it this way, it's a lot easier. A is equal to half of the second difference. That is a very important note. You should probably go ahead and put a box around that in case we don't talk about it explicitly again. But basically what that does is that gets us started when actually figuring out the rest of this function. Okay, so now we know that in this case, a is half of 6. A is 3. So f with respect to n in this case is 3n squared plus bn plus c. And now you look at that and you say, well, there's still two unknowns here, these unknown parameters. How do I figure that out? Well, turns out that we can actually create several algebraic expressions, equations, using this and using the values that we have here. Okay, so if we have corresponding x and y terms or domain and range terms, then we can start to fill in some of the blanks here, create two equations, and then solve for the unknown variables that way. Okay, so to determine the values of b and c, substitute, let's do this, create two equations with two variables by substituting the coordinates of 2 points. And those points come from n, t sub n, which come from our table of values. Now, why did I use this little phrase? To determine the values of b and c, create two equations with two variables. Because if you have the same number of variables and equations, you can solve for those variables. So if you have one equation that has two variables in it, you cannot solve for those variables, because as one changes, the other one can change. But if you have two variables and two equations, then you can use substitution and elimination in order to determine what those variables are and what they definitely are. They will not vary. They will have a specific value. Okay, so here we go. We're going to take two of our points. Let's take 1, 1. Then what does that tell us? That tells us that when n is 1, t of n is 1. So we're taking this formula here, and we know that, I'm going to use a colon there, not an equal sign. We know that 1, which is right here, our y value, if you want to think of it that way, is equal to 3 times the square of 1 plus b times 1 plus c. Okay. And we can rewrite that by simplifying it out. We've got 1 squared is 3. Sorry, 1 squared is 1. Times 3 is 3. So we've got, and I'm going to actually right away just group this. I'm going to subtract 3 from both sides. Okay, so we've got negative 2 is equal to 1b, which is just b, plus c. We're going to call that equation 1. Okay? And then we'll take our next easiest point, which is 2, 10. And that tells us that 10 is equal to 3 times the square of 2 plus b times 2 plus c. And again, we can simplify that quickly. We've got 4 here. 2 squared is 4. 12. 4 times 3 is 12. I'm going to subtract that from both sides. That gives us negative 2 on the left, is equal to 2b plus c. All right, So there we have two variables, b and c, but we have two equations, and we should see something very familiar from grade 10 math. We've got a system of linear functions here that we can solve. So let's go ahead and apply substitution or elimination. We're going to be using elimination in this case because it lines up nicely. And actually I was going to erase and rewrite, but I can probably just go from here. Okay, I can see I have one c in the top and one c in equation 2. So I'm going to subtract equation 2 from equation 1. So on the left here I have -2 minus -2. That's -2 plus 2. That's 0. I have b minus 2b. Okay, so 1 take away 2. That's going to leave me with a -b. And c take away c is 0. So here we get b equals 0. Now I think I'm going to have to pause and scroll up a little bit. So we built this b equals 0. That is 1 minus 2. And now we know that b is 0. So now all that's left is to find out what c is. And we know from equation 1 that -2 equals b plus c. So we know from equation 1 then that c is -2 simply by subbing in b equals 0 into either one of our equations. Okay, and then we can determine the value of c. So an explicit formula for the sequence is f of n is equal to 3n squared plus bn, b is 0, so that eliminates that whole term, plus c. c is -2. So we got 3n squared minus 2, where n belongs to the set of natural numbers. Okay, I'm just going to quickly describe why we have this each time. We haven't taken a note on it yet, but it actually comes up in the next example. If n from the domain can be from the set of real numbers, it can be any fraction or decimal number at all, then that actually creates a continuous function, a function that is here, 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 and everywhere in between. What we're dealing with in sequences, like the graph that we did originally, we didn't actually do our graph for b, but it ends up being a graph that jumps, right? It jumps from term 1 to term 2 to term 3 to term 4 to term 5 to term 6, okay? This is a discrete function. There is information not given in between term 1 and term 2. There's no such thing as term 1.5, okay? There's no such thing as term 3 3/4. Whereas the domain for this function is continuous, the domain from this function is discrete, it jumps. All right, just before we move on, we started with a given sequence. We created a table of values matching the term number with the value. Found the first differences, they weren't constant. Found the second differences, they were constant. That told us that it was going to be a quadratic function. We learned that a is equal to half of the second difference. So that gave us our first parameter there in our function. And then we were able to use two of the points. We could have used any of them. We could have used 325 and 446, but then it just gets bigger and uglier. We created two equations using two variables. We were able to use elimination in order to solve for one of the variables, sub that back in to get the other variable, which finished out our explicit function for us down here. All right, at the bottom of that page, or just at the very, very top of the next page, you should have space for a couple of notes here. We're just going to differentiate between the two different functions that I just talked about. So we've got continuous function, and then you'll have a similar size note on discrete function. So a continuous function is a function that maps real numbers to real numbers. So the sets, the numbers in each set, domain and range, come from the set of real numbers. It has, let's start a new line here. It has, or its graph, let's do that. Its graph is a curve with no holes or jumps. And that is different from a discrete function. Discrete function is a function whose domain is from the set of natural numbers and its graph is made up of separate points that are not connected. Okay, and you can think of a couple of examples of what could be graphed in a continuous function or what would be a discrete function. Maybe a continuous function would be you're measuring the height of a plant every week, okay? You only get these measurements from week 1 to week 2, but you're sure that it grows in between there, okay? It's a continuous process. Now, what about the second hand on a watch? Now, some of them are continuously going around, but a lot of them click, 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 click. And so if you had the position of the second hand as measured in degrees, okay, every second, every term would be distinctly different degree, and you would not connect the dots, okay? There's just a couple of quick examples. We're going to do a few more here in example 3. So in example 3, we have review of continuous and discrete. The charge in a battery decreases by about 2% per day and can be modeled by the function charge with respect to d, c with respect to d equals 100 times 0.98 to the power of d, where d is the time in days, c is the level of the charge as a percent. And the question is, how much charge is left after 10 days? Is this continuous or discrete? Well, if the battery power is gradually depleting, I'd have to say this is a continuous function. So that part's pretty straightforward. But now let's calculate how much charge is left after 10 days. All we have to do in A is sub d equals 10. Subbing d equals 10 into c with respect to d equals 100 times 0.98 to the power of d. So c of 10 is 100 times 0.98 to the power of 10. Click, 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 click. In your calculator, you get 81.7. So after 10 days, charge remaining, comma, charge remaining is approximately 82%. Okay, we already talked, it's a continuous function. It's going to go gradually. It doesn't drop 2 and then drop 2 and then drop 2. All right, B. A certain bacterial culture starts with 200 bacteria. It doubles every hour. Its growth can be modeled by the function n of t equals 200 times 2 to the power of t, where t is the time in hours, n is the number of bacteria. How many bacteria are there after 10 hours? Again, we just take the value that they've given us, which is t equals 10. So we're going to sub t equals 10 into n with respect to t equals 200 times 2 to the power of t. We want t equals 10. So we've got 200 times 2 to the power of 10. Click, 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 click. That would be 204,800 bacteria. So after 10 hours, there will be 204,800 bacteria. Now, is this discrete or continuous? A little bit tricky. You might think, oh, well, time is continuous. It keeps going. But the domain and range must be continuous. Now, can you have part of a bacteria? You cannot. So the values from the range are from the set of natural numbers, okay? So this is restricted by that fact, and this function is discrete. Since you cannot have part of a bacterium, this is discrete. This is a discrete function. And up here we had continuous function. As time progresses, the battery goes down continuously, the charge. We were also asked here to explain or to graph it. We could do that. We're not going to. But basically, this function, this graph, has the battery level going from 100 and going down 2% every day. And here, and by the way, I can use a line to show that it's continuous. Here we have a discrete graph and it's exponential. It starts at 200 and it might look something like this. Okay? Example 4, determine the value of a car. The value of a new car purchased for $78,000 depreciates at a rate of 15% in the first year and 4% every year after that. So we actually have a function that it's going to start at a value, it's going to drop significantly, and then it's going to drop by a percent. So it's going to be discrete. Here we go. Determine the value of the car at the end of the first year, at the end of the second year, and the end of the third year. Then write these values as a sequence. So we're not getting an explicit formula. We're going from one term to the next term. So in A, we can just jot down what we know. We have an initial value of $78,000. And then we have, for the first year, we're going to drop by 15%. So what's that going to do? That's going to give us 78. What's going to be remaining is 85% of the car's value. Okay? Which in our calculator gets us 66,300. So that's after the first year. Okay? Then I'll just put a big after. And after the second year, what's happening in the second year? It's going to go down 4%. So we're starting with 66,300. and we're going to lose 4%, so we're still going to have 96%, which is times 0.96. Click in your calculator, gets us a value of $63,648. In the third year, same thing is going to happen, down by 4%. So we're going to take our end value from the second year, which is 63,648. We're going to multiply it by 0.96 to keep 96% of the value. And we're going to get a value of 61,102.08. Now, another way that we could have done this third year is to simply take what we have here after the second year and multiply it by 0.96 again. So we actually could have taken 6630 times 0.96, put that in a group in brackets, that's what we're going to have at the end of the second year, and multiply that thing by 96% again. Okay, and that would get us this third value. Why do we say that? Well, that helps us to represent the value of the car as a sequence in order to generate our explicit formula, which we're going to have to do in B. So the sequence that we're given here, that we've come up with, the sequence for the first 3 years, is 66,300. I'm just going to leave a big space in between my numbers because I'm going to do another little thing underneath here. Then we have 63,648. And then the third term in the sequence here is 61,102.08. Now, how did we get those values? Okay, in this, after the first year, we're going to call this guy our new first term. And so he just is himself. That's just 66,300. Here, though, we have 0.96 times 66,300, right? That's how we got that value up here. And here we have 0.96 to the power of 2 times that original value of 66,300. And now you see we're well on our way to developing an explicit formula for any term in the sequence as the car vehicle continues to depreciate. So B, we can easily come up with an explicit value of the car at the end of year n for any value of n for any year, taking our original value, which is our first term, and we're going to multiply it by 0.96. And it's not going to be n times, because we notice that this is term 1, this is term 2, this is term 3. Here we have no factors of 0.96. Here we have one factor, and here we have two factors of 0.96. So we're actually raising this to the power of n minus 1. Whatever n is, we take away 1, and that's how many factors of 0.96 we have. That's how many years are passing from the value of 66,300 to the next value, okay? And C asks us to apply that. Basically says what, according to this model, what is the value of the car at the end of 20 years? Sub in 20. 66,300 times 0.96 to the power of 20 minus 1, which is, I'll write it all out for us, 66,300 times 0.96 to the power of 19, and click, 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 that value is approximately $30,525.79. All right, so that's what our formula says. The question asks, is that realistic? explain your thinking. So take a second to think about that. Is that realistic for that 20-year-old car to still be worth $30,000? Okay. A couple of things. It could be worth more if it were some specialty car or a vintage car or something like that, or if the owner took very, very good care of it, could be worth more than that. Could also be worth much, much less than that if it hasn't been taken care of properly, or it, you know, is in an area like us, and there's lots of commuting and travel, lots of mileage, and lots of salt eating away at your vehicle from the winters. Okay, so it could actually be worth much less, just considering the real world applications there and the factors. All right, folks, that's lesson 6.1. Your practice problems come from page 360, numbers 1 through 16. Enjoy.